Hello everybody, welcome back to CFD College. I'm Ashkan, and in this video uh, we are going to solve three problems on uh, linear momentum conservation. It's like a bit actually the problems we solved in previous tutorial, but here we have also a problem regarding a situation in which the control volume is not stationary, it moves. Okay, before starting this video, please subscribe the channel if you haven't done that so far. If you like these videos, give us a thumbs up. If you find them useful and helpful, please share them with your friends and let everyone enjoys these videos. Okay, let's jump to the first problem. Problem number 61. Okay, here we have a rocket. The rocket shown in the figure below is held stationary by the horizontal force Fx. Here we have Fx and Fz, and the vertical force Fz. The velocity and pressure of the exhaust gas are 5,000 feet per second and 20 psi. So at the outlet, we know that P pressure is 20 psia, means absolute. The velocity is 5,000 feet per second. The nozzle exit, which has a cross-section area of 60 inches per inches square. So the area is 60 inches square. The exhaust mass flow rate is constant at 21. So we actually know the mass flow rate of the exhaust, which is 21 lbm, pound mass per second. Determine the value of restraining force Fx. So we only need to find Fx. Assume the exhaust flow is essentially horizontal. So we have, as you know, the first step is to draw the control volume, which is easy because we only have these walls inside and we have only one outlet. So this is the control volume we have. We have only one control surface, CS1, which is outlet. So this is VE. We have two forces. This is Fx and also pressure. Don't forget that. PEAE. Why? Because we know the pressure and it's absolute. The value is absolute, so it's above the atmospheric pressure, and we have to include it. So that's it. These are the forces, control surface, and the control volume. The next step is to define axis. This is x. It doesn't matter where z-axis is because we only need to solve the linear momentum equation in x direction, since we should find only Fx. Okay, now the third step, the summation of forces in x direction equals to the change of momentum inside control volume, which is 0 since we are working at the steady state situation, plus the exchange of momentum rho Vx V dot N dA. Okay, so we have two forces. Fx is parallel to x axis, so Fx PEAE, force due to pressure, which is in the opposite direction, so minus PEAE equals, we only have one control surface over control surface 1 rho Vx is VE and it's positive, and V dot N, since here we have an outlet, it's equal to the magnitude with positive sign dA. So it's easy, it's equal to all of the variables are constant, rho VE, let me write it down this way, VE rho VE AE. Why we should do this? It's not it's not mandatory, since we don't know the density of the exhaust gas, but we know the mass flow rate. We should use this formula, as you know, m dot E equals rho VE AE, which is this term. So this term is m dot, this product of these three parameters is equal to mass flow rate. So Fx equals PEAE plus m dot times velocity. Okay, now we have the values. We can find Fx equals PE. PE is 20 psi, but its absolute value, it's pound force over inches square. We should subtract the atmospheric pressure, which is 14.7 psi, and P times area, which is 60 inches square. Since we have inches square in the numerator and in the denominator, there is no need to do a conversion, plus m dot 21 pound mass over second times velocity 5,000 feet per second, and we should convert LPM, so 1 over 32.2. Actually it's like this, 1 lbf over inches over 1 lbf equals 32.2 lbm times feet over second. So from this you can find Fx equals 5580 pounds. As you can see, it's not difficult and you can solve it easily. Let's jump to the second problem number 63. Water is sprayed radially outward over 180 degrees as indicated in the figure below. So the jet sheet is in the horizontal plane. If the jet velocity at the nozzle exit is 20 feet per second, so this velocity is 20 feet per second. The magnitude is actually, because the direction is not constant, it's radial actually, and determine the direction and the magnitude of the resultant horizontal enduring force required to hold the nozzle in place. Okay, so we have also the thickness of this outlet and the outer radius of the nozzle. So first step is drawing the control volume. It's like this. Actually, it's 3D. So if I wanted to show it to you, it's like this. This is the outlet. So this is the outlet. We know the velocity. There is no inlet, so this is the only control volume we have. We have two forces, Fx and Fy. So this is x direction and this is y direction, and we need to find Fx and Fy. From symmetry we can understand that Fy should be 0 because of the symmetry that we have in this problem, but we have to calculate it. So first, in y direction, the summation of forces in y direction equals the change of momentum inside the control volume, which is 0 since we are working at the steady state condition, plus cs, integral over control surface, which is only this outlet we have in this problem, rho vy v dot n dA. Okay, in y direction we only have one force, Fy, which is negative since it's in the opposite direction with respect to this coordinate. It's equal to, we have only one control surface, rho Vy. So this is y direction, and we need to find the velocity component in y direction. If this is this line, okay, this edge actually, here is the center. For example, at this point we have this velocity v1. We have to show the angle theta, which is this one. So you can start the theta from left and go counterclockwise, which is mostly used, but if you don't like it, you can use this notation and start theta from right and go clockwise. But the first one is more common. So in this way, here you can decompose velocity. This is v1y, which is equal to v1 cosine of theta. This is v1x, which is equal to v1 sine of theta. So by considering this, if we look closely to this control volume, let me name it dA. This is the control volume we have. This is dA, and so we want to solve it. We should actually consider this differential element, because now we have this theta, which is not constant. You will see this. So let me, okay, we don't need it. So f minus fy equals integral over cs1 rho vy, which is, this is y direction, and you have to be careful, since v 1 cosine of theta is negative, since it's towards left, y direction is towards right. So minus v1 cosine of theta, and v dot n equals v1y. This is v1, because we have outlet, and the only thing that matters is the magnitude. What about dA? This dA, here you can see this is d theta. This is r. This is r. And this dA, as you know, this is the thickness, which is delta. So dA or h, let me name this h. dA equals r pi r d, okay, no, it's not right. It's h r d theta. This is d theta times r. We have this length, and if we multiply this by the thickness, we will have dA, the area. Okay, we have everything. So h r d theta, which is dA, and as you can see, theta is not constant, but rho, v, h, and r are constant. R is equal to 8 inches. So minus fy equals rho minus, this is this minus v1 square hr integral of cosine of theta d theta from 0 to 180. So from 0 to pi. So you know how to deal with this integral. It's easy. So fy equals rho v1 square hr, integral of cosine is sine of theta from 0 to pi. and this is equal to sine of pi minus sine of 0. Both are zeros, so this is 0 and this is 0. So this equals to 0. So Fy, as we expected, is equal to 0. Let's deal with x direction to find Fx. So the summation of forces in x direction, I don't write the first term, equals to the exchange of momentum through contour surfaces, rho Vx v dot n dA. So in x direction, we only have this Fx and it's parallel to x. So Fx equals over contour surface 1, rho is constant, Vx is V1 sine of theta, and V dot n is equal to positive V1. Why? Because we have outlet, and for outlet V dot n is positive. dA is the same, so hr d theta. It's equal to rho V1 square hr integral sine of theta d theta from 0 to pi equals rho V1 square hr integral of cosine sine is minus cosine from 0 to pi. It's equal to rho V1 square hr times minus cosine of pi plus cosine of 0. So this is 1, this is minus 1, we have another minus, so it's positive 1. So it's equal to 2 rho V1 square hr. And now you can solve this problem. Fx equals to rho 1.94 slugs per cubic feet. V1 square, V1 the exit velocity, which is 20 feet per second square, times h, the thickness 0.5 inches, 0.5 divided by 12 feet, don't forget that. R is 8 inches divided by 12 to get feet. And in the end, the conversion for slug, 1 pound is 1 slug feet per second square. So Fx equals 43 pounds. This was the second problem, and we have another problem number 80. Let's see what we have. A snowplow mounted on a truck clears a path 12 feet through heavy wet snow. Okay. As shown in the figure below, the snow is 8 inches deep. So this is the depth of the snow, and its density is 10 pound mass per cubic feet. So we have the density. The truck travels at 30 miles per hour. The snow is discharged from the plow at an angle of 45 degrees. This is the angle. Here is the speed of the truck from the direction of travel and 45 degrees above the horizontal. Okay. Estimate the force required to push the plow. So first we need to draw the control volume. It's obvious that the control volume should be like this. This is our flow. Forget about the snow. Think that you can think this problem is a simple water jet, for example. So this is the control volume. This is the vane, for example, and here we have the jet entering the control volume, and here is the outlet. But this is what happens on the snow. It's like that we have this inflow of the snow, and here is the outlet. So this is the control volume we have. But in this example, in this problem, the control volume is also moving with 30 miles per hour, and this is the direction. So let's indicate our control surfaces. This is CS1, the inlet. This is CS2, the outlet. So this is the inlet, this is the outlet, and we have Fx, which is this force. Since we have a moving control volume, we should use another form of linear momentum equation, which is this one. The summation of forces equals W rho W dot N dA. W is relative velocity. Remember that we are working in the steady state condition. That's why you don't see the transient term. And know that W is relative velocity, which is W equals V minus velocity of control volume, and these are vectors. Okay, so here we don't have V, we have W1, and at the exit we have W2. Don't work with V velocity. We should work with, don't work with absolute velocity. You should use relative velocity. Okay, this is X and this is Y direction, the second step. And since we want to find Fx, which is horizontal, we should solve this equation in X direction. So summation of forces in X direction equals the exchange of momentum with Wx. It's pretty similar. W dot N dA. So we have only Fx minus Fx, because it's in the opposite direction, equals, we have two control surfaces over control surface 1. Wx is W1 rho. Since we have inflow, we have inlet, it's minus W1, and dA plus over control surface 2, we have W2x. So this is I'm sorry, I'm a terrible drawer. This is W2, this is X and Y direction, and you have to find the component of velocity W2x, which is this is 45 degrees. This is W2 cosine of 45. Remember, you need negative sign here because it's in the opposite direction. So minus W2 cosine of 45, and rho we have outlet, so W2 dot n is equal to W2 dA. Okay, so what we have, minus fx equals minus rho a1 w1 square minus rho a2 w2 square cosine of 45 degrees. But since we know that the mass flow rate or the volume flow rate is constant, I mean m dot 1 equals m dot 2 or q1 equals q2, we know that from these that a1 w1 equals a2 w2, and since we don't know anything about the thickness of this snow at the outlet, we can assume that a1 equals a2, and with this assumption we can understand that w1 equals w2. So fx equals rho a w1 square plus rho a1 w1 square cosine of 45 degrees. So fx equals rho a1 w1 square 1 plus cosine of 45 degrees. Now we should find w1. The snow here doesn't have any velocity. Actually, it's on the I don't know, on the ground. So if we want to find w, we have to write down this. W1 equals v1 minus vc, and these are vectors. So since snow doesn't have any velocity, it's a stationary, v1 is 0. This is x direction. Here is the direction of the vc. So as you can see, they are in the opposite direction. So w1 equals minus vc, but control volume velocity is in the opposite direction. So minus 30 mph equals 30 mph. So we have the velocity. Now we can solve the question. Fx equals density, we know that 10 lbm cubic feet. We have to convert it. 1 lb f equals 32.2 lbm feet per second square. A1 equals 8 inches times the width. The width is 12 feet. So 8 inches, 8 over 12 feet, and the width is 12 feet. W1, we found it. It's 30 miles per hour. We should convert it. Every 5,280 feet is 1 mile, and every 1 hour is 3,600 seconds square times 1 plus cosine of 45. So fx can be found as 8,220 pounds. So as you can see, it wasn't difficult. It's tricky, but it's not difficult. So this is the end of this video. Thanks for watching this video. I hope you find these videos useful. If so, please subscribe the channel. You can enjoy other videos that are available in my channel. They are about CFD, numerical simulation, post-processing, drawing different charts. And don't forget to share these videos with your friends. Thanks for watching. Until the next video, take care of yourselves and bye bye.